So we just are looking for when does this increase, when does this decrease, maximum, minima, points of inflection, and when it's concave up and concave down, right? I think that's all I'd ask for on the homework.
Yes.
Is that right? Okay, cool. So in order to do that, we're obviously going to need a derivative and we're going to need a second derivative. And one of the other important things that we want to look at is what the domain of the function is, because that really sort of is going to have a pretty big effect on critical values some of the time. So let's think about the domain of this. We know that natural log has to be, when you take the natural log of something, that thing that you take the natural log of has to be a positive number, right? You can't take the natural log of a negative, and you can't take the natural log of 0. So if we're looking at the domain of our original function, that ought to tell us that x squared minus 1 has to be positive, right? If it's not positive, we can't take the natural log of it. So in other words, x squared is greater than 1. Or if x squared is greater than 1, that means that x is greater than 1, or x is less than negative 1. So effectively, we've got a domain of negative infinity to negative 1 union 1 to infinity. We've got just a big gap in our graph between negative 1 and 1. Everybody okay with that?
Yes.
Okay. So then from there, when we start taking our derivative, first thing we got to do is we got to take our first derivative. So if this is y equals natural log of x squared minus 1, then our derivative y prime ought to be, well, natural log of u is 1 over u times the derivative of u, which is 2x, right? And so when we go in there and see when this equals 0, the only place where this would equal 0 is when the numerator equals 0, which would be if x equals 0, right?
Yep.
Okay. And the only time this would be undefined if
Plus or minus 1.
Right, if x squared minus 1 equals 0, which is x is plus or minus 1. And so a critical value has to be a point that's actually defined on our original function. And the 3 potential critical values that we got here were positive and negative 1 and 0. Well, if we look over here in our domain, none of those are in the domain, right? Because we don't include negative 1 or 1, and 0 is between negative 1 and 1. So there are no critical points for this function, which doesn't necessarily mean that the function is always always increasing or always decreasing. It just means that for each piece of its domain, it's either always increasing or always decreasing. So what we want to do is we want to make a sign chart still, and we're going to put negative 1 and 1 on it, and we can just sort of ignore all this junk in the middle because there's no function there. And all we need to do is plug in a number more than 1 and a number less than negative 1 so that we can see what's happening on each side of this. Does that make sense so far to everybody?
Yeah.
Okay. Cool. So if we plug in something greater than 1, like, I don't know, 1,000, 2 times 1,000 is a positive number, and 1,000 squared minus 1 is a positive. So we have a positive over a positive gives you a positive, and we know that our function is increasing on that interval. Good or no?
Good.
Good. Okay. We plug in a negative number like negative 1,000. We end up with a negative over a positive, which is a negative, and we have our function is decreasing. And so there's no endpoint to the left, right? And this is just going from negative infinity, right? So there's no endpoint to the left. And there's no endpoint here at negative 1. So there's no way for me to have a local max or a min on that side. And the same thing over here, and it's always increasing over here, but there's no endpoint at 1, and there's no endpoint at infinity. So we're not going to have any local max or min on that side either. So all we can say is no local max or min, and we can list the intervals on which it's increasing and decreasing. Does that make sense?
Yes.
We'll say it's increasing from 1 to infinity, and we'll say it's decreasing from negative infinity to negative 1. And I know that way back when we first started talking about this, like 3 days ago or something, that I said always include the numerical endpoints if they're real numbers with brackets. So I should have been a little more specific about that, as long as that point is actually included in the original function. But 1 and negative 1 are not included. They're not in the domain of our original function. So we have to leave those as open parentheses. So if it's an endpoint, or if it's a point that is included in the domain of the function and it's a real number, put it in brackets. Otherwise, if it's infinity or a point that is not included in the domain of the original function, put it in parentheses. So everybody okay with the first half of that before we look for points of inflection and concavity?
Yep.
Yes.
All right, cool. So in order to find concavity intervals and points of inflection, we need to find a second derivative. So our first derivative was 2x over x squared minus 1. So our second derivative, we'll just use the quotient rule. Okay, quotient of two functions. So we have denominator, derivative of numerator, minus numerator, derivative of denominator, all over denominator squared. Good or no?
Good.
All right, so simplifying out our numerator gives us 2x squared minus 2 minus 4x squared over that x squared minus 1 squared, or negative 2 minus 2x squared over x squared minus 1 squared. And even if we wanted to, we could take a negative 2 out of the numerator. So that would give us negative 2 times x squared plus 1 over x squared minus 1 squared. Good or no?
Good. Yeah.
Okay, great. So first off, this is undefined where x equals still plus or minus 1 from the denominator. And when does this equal 0? If the numerator is 0, right? Well, negative 2 is never 0. So in order for the numerator to be 0, x squared plus 1 would have to be 0. And when does x squared plus 1 equal 0?
The square root of -1.
Square root of -1, right? Which we know is the imaginary unit, right? It's not actually not actually any real values there. So we'll say that never equals 0 on the real numbers. And so once again, here we don't ever have anything from the numerator, and from the denominator, to make it undefined, we have 1 and -1, but both 1 and -1 are not in the domain of my original function. So I will say there's definitely no points of inflection. And we'll just make a similar sign chart to what we did before, -1 and 1, but we'll get rid of all this junk in the middle because our function doesn't exist there. And we'll see if our function's concave up or concave down on either side of it. And it could be one on one side and the other on the other, or it could be both concave up or both concave down. So we plug in a positive number like 1,000. Our numerator is definitely positive times a negative, so definitely a negative. And then our denominator, which is squared, is always going to be positive. So this ought to be negative. And if we plug in a negative number, well, that negative number squared plus 1 is positive, times this negative is negative, and then something squared is always positive, so we have, again, negative, which tells us that this function is concave down from negative infinity to -1, union 1 to infinity. No points of inflection, and we would say never concave up. Good or no?
Good. Thank you.
Yeah, no problem. And so just real quickly, I think I have Desmos open already. Yeah, so let's take a look at what this function looks like and make sure that what we did is correct. So we said, and sure looks like, even if I zoom out on this, right, it sure looks like there's never any points here in between -1 and 1. True. And our function is decreasing from -infinity to -1 and increasing from 1 to infinity. And this is concave down, and this is concave down. So it looks like everything that we got there seems to match up with what the graph looks like. Good or no?
Good.
Wonderful. All right. Spectacular. Any other questions on this or the homework or just anything else in general that we've been talking about in the last 4 weeks, I guess?
So when we're doing intervals of concavity, does College Board want us to use parentheses or brackets?
They want parentheses no matter what. Anytime you're doing concavity, always parentheses on any number that's in concavity. And then increasing and decreasing, they want brackets on real number values that are in the domain of the original function. Any other questions, anyone? All right. In that case, let's move on to what we're going to talk about today. We're going to talk about 2 different things today. The first of those is called the mean value theorem. And I thought I had I don't know why I have, oh, this is what we already, I already had this open. That's why. I was confusing myself. All right, the mean value theorem is the first thing we're going to talk about today. So, mean value theorem is just a little theorem that has to do with derivatives. So it's kind of like another little basic application of derivatives. It's got some small applications, but the main application that we're going to talk about with it is something at the end called Rolle's theorem. But the mean value theorem just says that if you have a function and that function is continuous on some closed interval, we'll say from A to B, and the function has a derivative at every point on that interval, so it's differentiable on the entire interval from A to B, the open interval from A to B, so you don't have to be able to take the derivative at the endpoints, then it says that there is at least one point, and we call that point C, somewhere on the interval between A and B, where the instantaneous rate of change, or the slope of the tangent line, is exactly equal to the slope of the line that goes through the 2 points at A, f of A, and B, f of B. So the instantaneous rate of change, the slope of the tangent line, is equal to the average rate of change, the slope of the secant line. Okay. That's what the mean value theorem says. And so the effective formula for that is f prime at C is equal to f of B minus f of A over B minus A. So it's the slope at some number C is equal to the slope between A and B. Does that make sense? And we see where this little formula comes from, or no?
Makes sense.
Okay, so let's just for fun. Here's some random function. Here is a point at A, and here is a point at B. There is the line that goes through those. This function is continuous from A to B, true?
Sure.
And the derivative exists everywhere between a and b. Because remember, there's only 4 reasons why a derivative might not exist. One is a discontinuity. Don't have one of those. One is a vertical tangent line. Don't have one of those. One is a corner. Don't have one of those because this is not doing that. And one is a cusp, which would be like that. Definitely don't have one of those either. So the function is continuous on this interval and it is differentiable on this interval, which tells you that somewhere on this interval, there's a place where I bet it's about right there, where the slope of the tangent line is exactly the same as the slope of that secant line. Now, it doesn't necessarily mean that that's the only place where that could happen, and for this particular one it is. But suppose I'd drawn my a to be like right here, right? Instead of using this value, I'd gone from a to b like that. Pretend that is nice and continuous there now. That looks good enough. All right, so there might be a second place, right? There might be a place over here where the slope of the tangent line is the same as the slope of that secant line through those 2 points. Okay. But it's at least guaranteed that it will happen one time between A and B. Maybe more than once, but at least once. Good or no? Conceptually, we understand what this should look like and sort of the idea of it all?
Yes.
Okay. Wonderful. So that being said, I just want to make sure that you recognize that when you are asked to verify the mean value theorem or use the mean value theorem for something, that you always remember the first thing you have to do is check to see that f is continuous and that f is differentiable on that interval. If it's not, the mean value theorem doesn't apply. And they like to sometimes ask you to use the mean value theorem for something in which it hasn't met those hypotheses. And then you will have to say the mean value theorem doesn't apply because it's not continuous or because it's not differentiable on that interval. So make sure you check that it is continuous on the closed interval from A to B and differentiable on the open interval from A to B. So if we think about a function, for example, something like absolute value of x, right? That's absolute value of x, approximately, right? And let's say we were talking about the interval from -1 to 1. Well, is this function continuous on that interval?
Yes.
Is it differentiable on that interval?
You can't differentiate it at x equals 0.
Right, we cannot differentiate it at x equals 0. There's a corner there, no derivative there, derivative doesn't exist. So the mean value theorem doesn't apply, right? MVT doesn't apply because it is not differentiable. Okay. And we would note that if we chose the points between -1 and 1, what's the slope of the line? Oh, that was really poorly drawn. What's the slope of the line between -1, 1, and 1, 1?
Zero.
Yeah. And so if the mean value theorem were to be if we attempted to apply it, even though we can't, that would tell us that somewhere between -1 and 1, the slope of the tangent line would be 0. And well, clearly everywhere from here to here, it's -1, and everywhere from here to here, it's 1. And at this point, the derivative doesn't exist, and therefore can't be 0 either. And does that make sense?
Wait, so is it like if you have one point where you can't differentiate it, you can't use the theorem at all? Or
That's correct. You cannot apply the theorem. It doesn't necessarily mean that there might not be a point where the slope of the instantaneous slope and the average slope are the same. There still could be, but it's just not guaranteed by this theorem. And so we can't apply the mean value theorem to find it. We can still see if there is one by applying, by just by using the formula to see if there's a solution to this equation. But we couldn't do it and say that we were guaranteed that it was true because of the mean value theorem.
Okay. Thank you.
And so a lot of times they might just do something like give you a chart of values and say something, and we'll practice some of these when we come back for our fourth quarter, a little before the AP test, but we'll practice some of these where they say, here's a chart of values. What theorem says that the instantaneous slope must be 7 on this interval? And explain why. And you'll be like, well, because the average rate of change on that interval is 7, and you told me that this was continuous and differentiable, so the mean value theorem for derivatives says that, that kind of thing. But we'll do that. We'll do that later on. We'll worry about that another day. You guys know what this function is? int, the greatest integer function of x. Sometimes seen written as double brackets. You've seen it before. You just may not remember the name. Step function. That function look familiar? Oops, forgot to fill in that one. Does that look familiar or no?
Yes.
Okay, yeah, good. The greatest integer function, step function. Okay. This function is the greatest integer less than or equal to x. So plug in 0.5. The greatest integer that's less than or equal to 0.5 is 0, all the way up to 0.99999. The greatest integer less than that is 0, and so on. So this one, the mean value theorem, wouldn't apply for what reason?
It's not
It's
continuous.
discontinuous.
It's not continuous, exactly. And I think we could do a similar thing about checking over here to see if there was a place where it was true, but we don't need to bother with that, I don't think so. Just recognize that if it's not continuous or not differentiable on the interval, mean value theorem doesn't apply. So let's see if we can take a nice, simple, easy function and check if it satisfies the hypotheses of the mean value theorem, and then find all of the values on the interval 0 to 2 that I'm giving you where the derivative does equal the instantaneous rate of change. All right, so you remember when I told you a day or two ago that 99% of the time for the rest of this unit, the answer to what are we going to do first is going to be take the derivative? Remember when I said that? 2 days ago? Yeah. Okay, so what are we going to do first here?
Take the derivative.
No, this is the 1% where we're not going to do that first. Okay. I just wanted to make somebody be wrong because that was fun. First person that was wrong was my kid who yelled from down the hallway, take the derivative. He was wrong also. So the first thing we have to do is make sure it satisfies the hypotheses of the mean value theorem. Then we will take the derivative. So don't worry, there's still going to be a derivative in here. So what's the first hypothesis of the mean value theorem? That the function must be continuous on the closed interval 0 to 2. And why is it? Why do we know that this function f of x equals x squared is continuous from 0 to 2? What knowledge about this function tells us that?
It's a polynomial.
Right. So we'll say it's continuous because it's a polynomial. And does f prime exist on the open interval 0 to 2? Should say yes, it does. And the reason why is because it is a
Polynomial.
polynomial. All right, so we have now satisfied the hypotheses of the mean value theorem, which means we can actually go and try and apply the mean value theorem. So f is continuous on the closed interval 0 to 2 because it's a polynomial. F prime exists on the open interval 0 to 2 because it's a polynomial. So therefore, by the mean value theorem, f prime of c needs to equal f of b minus f of a over b minus a for some c on the interval 0 to 2. So the question is then, what is the solution c to that equation? And so what, first off, is f prime of c?
2x.
Well, almost. F prime of c would be 2c, right? But yeah, derivative of x, or f of x is 2x, so f prime of c is 2c. And what's f of 2? Should just be 4 minus 0 over 2, or 2c equals 2, or c equals 1. And so we would get that the solution to this is c equals 1, or an x value of 1. And that's the place where the tangent line is parallel to the secant line through 0, 2. And let's write the equations of both of those lines. So if I have a line that goes through the point 0, 0, and has a slope of, what is the slope going to be? What's f prime of 1? Or what is this slope? We should have got a slope of 2, right? So one of these equations should be y equals 2x for the one that goes through 0, 0. And for the one that goes through the point 1, 1, it should be y minus 1 equals 2 times x minus 1. So there's our tangent line equation. There's our secant line equation. And if we were to go in and take a look in Desmos, we would see that when we graph this, there's our parabola. There's y equals, sorry, not y equals x, y equals 2x, right? And then y minus 1 equals 2 times x minus 1. And we can see that, first off, our y minus 1 equals 2 times x minus 1 is tangent at 1, and it has a slope of 2. Okay? And y equals 2x clearly goes through the points 0, 0, and 2, 4, the endpoints of that interval, also has a slope of 2. And clearly, I mean, they both have a slope of 2, but you can clearly see that those two lines are parallel. Good or no?
Just checking again, where did you get the slope of 2?
Well, I got it from, there's two different places I would have got it from. So one, and first off, we know that it should be the same for both of them, but one was this f of b minus f of a over b minus a. That's the slope, or that's the slope formula, y2 minus y1 over x2 minus x1. So that came out to be 4 minus 0 over 2. It came out to be 2. So that was how we knew the slope of the secant line was 2. And f prime evaluated at 1, right? F prime of 1 should be 2x evaluated at 1, or 2 times 1, or 2. So we know that the derivative should give us 2 at the same, or on the interval in which the slope formula gives us 2. Does that make sense or no?
Yeah, I think so. Thank you.
Yep. Any other questions on that? All right, let's take a look at these two and see if we can figure out why both of these fail to satisfy the hypotheses of the mean value theorem. So let's take a look at square root of x squared plus 1. First off, is this continuous? On our interval from -1 to 2? Yeah, it should be, right? I can plug in any number to that because I can square root anything as long as that thing is positive or 0. And the squared in there is going to allow me to make anything inside of there positive. Right? So we know that f is continuous on this interval -1 to 2. But what about differentiable? So the derivative of this, f prime, ought to be 1/2 root x squared times the derivative of x squared, or x over 2 root x, or sorry, x over root x squared. Right? And can I have this exist for every value between -1 and 2? No, f prime does not exist at x equals 0, right? So this one fails to satisfy the second part of the hypothesis, that it has to have a derivative that exists on the entire open interval. And we don't have that, right? 0 is between -1 and 2, and our derivative doesn't exist at 0. Good or no?
I'm good.
All right, what about this this other one? X cubed plus 3 is continuous, right? And x squared plus 1 is continuous. The question is, do they meet up nicely at x equals 1? And the answer to that comes from a left and a right hand limit, just like we did a few weeks back. As we approach 1 from the left, what is f of x? From the left, that'd be x cubed plus 3, so that'd be 1 cubed plus 3, which is 4. And what about as we approach 1 from the right? That'd be x squared plus 1, which is 2. And if the limit from the left doesn't equal the limit from the right, that tells us that the limit as x approaches 1 of f of x does not exist. And based on that, that tells us that this function is not continuous on -1 to 2. Right? Because the definition of continuity says that the limit has to exist as one of the 3 criteria for a function to be continuous at a point. Good or no?
Good.
All right. You guys want to try and work on this one on your own for a minute and see how you can do?
Yes.
All right. Ready to go. Maybe 3 or 4 minutes here. Does this satisfy the hypotheses of the mean value theorem? We guaranteed that there should be one that is parallel to this secant line. Is f of x continuous? On -1 to 1?
Yes.
Yep, should be. What sort of graph does this actually look like? This is a semicircle. This is a graph you should know, right? I'm just going to real quickly off to the side here. Y equals √1 minus x squared. If I square both sides of that, I can get x squared plus y squared equals 1. Right? The positive square root is the upper half of the semicircle, and the negative square root would be the lower half of the semicircle. And in fact, let's just real quickly, right? We know x squared plus y squared equals 1, right? That's the circle. Well, square root of 1 minus x squared is just the upper half of it. And if you were to throw a negative in front of it, to get you the bottom of it. So positive square root, negative square root, positive square root, negative square root, positive square root, negative square root, positive square root. That's what we've got, right? Is positive square root. So you should know that graph. And so just by looking at the graph, we should know that f prime of x exists on the open interval -1 to 1, because there weren't any corners, cusps, vertical tangent lines, or discontinuities. So we could say basically for the same reason, but we could also just take the derivative to see that. 1 over, we'll say f prime equals 1 over 2 root 1 minus x squared times the derivative of negative x squared. So we get negative x over root 1 minus x squared. And the only value that would make these things be undefined is numbers that are greater than or equal to 1 or less than or equal to -1. And none of that is on this domain. This is the open interval from -1 to 1. So the fact that this is undefined at 1 is okay. And the fact that it's undefined at -1 is also okay. Good or no?
Wait, sorry. How did you find the derivative of this again?
Using the chain rule, right? So this is root u with u equal to 1 minus x squared. So 1 over 2 root u times the derivative of u. Does that make sense or no?
Okay, I see it now.
Okay, cool. All right, any other questions with that so far? All right, so there's our derivative. And we know that it needs to be parallel to the line that goes through -1, 0 and 1, 0. So that'd be 0 minus 0 in the numerator over 1 minus -1 in the denominator, or 0. So effectively, we're wondering, when does negative x over root 1 minus x squared equal 0? Well, that answer would be at x equals 0. And so we would say that at x equals 0, it has a slope of 0, and that's where the tangent line is parallel to the line that goes through -1, 0 and 1, 0. What's the line that goes through the points -1, 0 and 1, 0? If it goes through this point and this point, it ought to be just a horizontal line, right? Y equals 0. Yeah. And if it's parallel to that and it goes through the point 0, 1, that equation should just be y equals 1. Tangent at 0, 1, horizontal, parallel to the one that goes through 1, 0 and -1, 0. Good or no?
Good.
Wonderful. All right. Any questions at all from anybody so far? So we ended up here with y equals 1 as our equation. Okay. Last little thing we're going to add to this is just a little corollary to the mean value theorem. And that corollary is called Rolle's theorem. So Rolle's theorem has the same starting out hypotheses of the mean value theorem, that the function must be continuous on the closed interval and open on the, and differentiable on the open interval. But it also says f of a equals f of b. So if f of a equals f of b, like for example on the one we just did, didn't f of a equal f of b? They both equaled 0, right? F of a equals f of b. What is that going to tell you? If f of a equals f of b, the average rate of change is going to be
0.
Yeah, it's going to be 0. And so if the average rate of change is 0, that tells us that the derivative is going to equal 0, according to the mean value theorem. And so this is a special case of it called Rolle's theorem. And we know that a time when the derivative equals 0 is also called a critical value. So if the function is continuous on the closed interval, differentiable on the open interval, and f of a equals f of b, it tells us that there must be a place on this interval where the derivative is 0, or a place where there is a critical value. Does that make sense or no?
Yes.
All right, cool. So let's see if this function, 4x squared minus 20x plus 29, satisfies the hypotheses of Rolle's theorem on the interval from 1 to 4. So first off, is f continuous on 1 to 4?
Yes.
Yep, and why? Because
It's a polynomial.
it's a polynomial. What about f prime? Does f prime exist on the open interval from 1 to 4?
Yes.
And why?
There's a derivative.
Say that again? Sorry, I didn't hear you.
There's a derivative that's also polynomial.
Yeah, the derivative is also a polynomial. Exactly. Okay, good. And so the next thing we'll need to check is, does f of 1 equal f of 4? So what's f of 1? 4 minus 20 plus 29? Or 13? And what's f of 4? Should be 64 minus 80 plus 29, which is, again, 13. So criteria 1, criteria 2, criteria 3 have all been met. So we'll say by the mean value theorem, there is a critical value on the open interval from 1 to 4. And we should be able to find what that critical value is by taking the derivative, f prime, evaluating it at c, and setting it equal to 0. So what's the derivative of our function? Should be 8x, or if we're evaluating it at c, 8c minus 20. And that should equal 0 when c is 20 over 8, or 5 over 2. Good or no?
Good.
Any questions on that?
So when you're trying to find whether or not it's differentiable within that interval, you just find the derivative.
Yep. And as long as you can plug every value between 1 and 4 into that derivative, then you know that it's differentiable on the interval. And since our derivative here, since our original function was a polynomial, its derivative is going to be a polynomial or a constant. And therefore, you'll be able to plug anything in. As long as your original function is a polynomial, there'll be no issues. If they're, like the previous one, our original function wasn't a polynomial. So we sort of needed to look at it once we took the derivative. And we said that, when we took the derivative of it, we got negative x over root 1 minus x squared. The only things that make this undefined would be numbers that are greater than 1 or less than negative 1. And that wasn't in, isn't in the domain of what we're looking at. We're looking from negative 1 to 1. So does that answer your question or no?
Yeah, that answered it.
Okay.
Also, you said that there are like 4 reasons why it might not be differentiable. So is that like the original function doesn't exist at that point, or like it has like a corner or a cusp or something?
Yep, those were the, yeah, so when we first started talking about derivatives, I gave you 4 reasons. So one was a corner, one was a cusp, one is a vertical tangent line, and then the last one is the function has a discontinuity.
Okay, thank you.
Yep, no problem. Any other questions on that? Okay. I was going to start the next little lesson, but we've only got about 7 minutes left, and I won't really even have time to get into it at all. So I think we're just going to stop there and be done a couple minutes early. Just means we'll have a little bit more to do tomorrow, but that's okay. Anybody have any other questions on anything we've done today?